This video covers topic 8, section 5, which is titled Margin of Error. So in this lesson, students will be able to evaluate reports estimating population parameters, use multiple samples to make an inference about a population, and calculate the margin of error for quantitative or categorical data. So we're starting with looking at estimations of population parameters by finding sample statistics. So Seth selects a random sample of students from a local college and asks their year in college and how far the college is from their home in miles. So he's asking each student 2 different questions: what year they are in college and how far they live from the college. Oh, I'm sorry. And so we're asked 2 different questions. They want us to estimate the proportion of freshmen in the population, and they want us to use SES data to estimate the mean distance from home. So if we're looking at the proportion of freshmen in the population, all we really need to do is count how many freshmen there are. So in the sample, there are 1, 2, 3, 4 freshmen. So we're going to take 4 out of how many people is in the sample. So if I count how many people there are total, there's 20 people in the sample. So if I divide 4 by 20, that's 1/5, which is 0.2. Or I could write that as 20%. So based on Seth's sample, 0.2 or 20% of the college is freshmen. The next thing we're going to do is use Seth's data to estimate the mean distance from home. And so what that means is that we're going to take all of the numbers, because those represent their miles from home, and we're going to add them all together. So we're going to add each of those 20 data points together and see what the average distance from home is for this sample of students. So if I add up all those numbers, I get 2,017. Remember that there's still 20 people that he talked to, so we're dividing that by 20. So if I divide 2017 by 20, that gives me about 100.85, and this is miles from home. So the average distance from home that a student in this sample is 100.85. So the accuracy of estimates using sample statistics. So the accuracy of an estimate depends on the number of participants in the sample. So the number of participants in the sample and how well the sample represents the population. So it's not just that the bigger my sample is, the better my sample is, the more representative of the actual population is, the better my sample is. So for example, if I know what the actual percent of freshmen, sophomores, juniors, seniors are in the college, which is information that should be readily available, then I should make sure that my sample contains that same disbursement. Something similar with gender. So we can think about if I'm looking at a certain split for gender, I should make sure that my sample represents a mirror of that split. And so ultimately what's happening is that a larger sample will provide more accurate estimates than a smaller sample. So the larger the sample, the more accurate the sample is. If by chance the sample clusters away from the true mean, estimates will not be very accurate. So we are flipping a coin here, right? We're choosing a group of people that we hope best represents the population, and it could be that we just pick a bad sample. So that's why something called a sampling distribution is a better way to collect data. So this is collecting a variety of samples and then finding the averages of those samples. So the distribution of sample statistics, such as means or proportions from different samples of the same population. So the more samples that we take, the more accurate our results will become if we average those things together. So in example 2, Tia is contributing to the same project as Seth and has sampled a different groups of students. So Tia has the same questions. She's asking students, and we're going to look at first the proportion of freshmen in Tia's sample. So if I look at Tia's sample, which also has 20 people in it, she talked to 1, 2, 3, 4, 5, 6, 7, 8 freshmen. So she talked to 8 freshmen out of the 20 people she talked to. And so that's a 2/5. So she talked to double the amount of freshmen as Seth did, which means that her statistic is 0.4 or 40%. So B is saying, how can Seth and Tia determine whose result is a better representation of the population? And so ultimately, we're giving you the answer here because this is a new concept. So Tia and Seth decide to examine more samples, 50 total samples of 20 college students. So they take their 2 samples, right, and they do 48 more. So now they have 50 samples, all the same setup where they're talking to 20 students. And then they create a sampling distribution. So that means that they calculate out the proportion of freshmen in each of the 50 samples, and they use a histogram to represent that data. So they have 50 different proportions, and then that's represented in this graph. So by the empirical rule, one thing that we need to think about is where the majority of the data lies. So by the empirical rule, the majority of the data and we're going to look at specifically that 95% mark on the empirical rule, is between 2 standard deviations from the mean. So if we're looking at our graph where the mean should lie in the middle of this histogram. So the mean is somewhere between in this section, because that's where the peak is of the histogram. So the mean is between 0.2 and 0.25, so somewhere in that range. And so thinking about that, if the mean is there, remember that the 2 standard deviations would mean that I'm looking at this chunk as the 95%, 2 standard deviations between the mean. So that's between 0.1 or 10% and 0.35 or 35%. So if we think about what we looked at in terms of their data, with their data, Seth's mean was here. So Seth's proportion was 0.2, and Tia's proportion was 0.4. If we look at on our graph, 0.4 technically doesn't even have any values because this goes from 0.35 to 0.39999, right? It's all the way up to 0.4. So looking at this, which of the 2 is closer to the mean based on this distribution? So they took 50 samples of 20 more students, and they found the proportion of freshmen. Seth's value is closer to that, where that true mean should lie, somewhere between 0.2 and 0.25. So that means that Seth's result is more likely to be accurate because it is closer to the mean in the sampling distribution while Tia's is outside the range of reasonable means. Remember, that's that 95% marker. So test result is more likely to be accurate because it's closer to the mean of that sampling distribution. Okay, so now we're going to move on to looking at not using multiple representations by collecting more data, but by using a random numbers to help us mimic a study. So Gabriella wants proof that Alex's claim that he is a 75% free throw shooter. She observes Alex shoot 50 free throws, of which he makes 30. So that's a 60% success rate, not 75. But Alex points out that this is a reasonable result due to the natural variability and happens from sample to sample. So he's saying, yeah, my average is 75, like that was just a low one. And so what Gabriella does then is, so we're looking at random numbers to investigate his claim. So to see if it is actually a reasonable result, finding that 95% sample. So they used a random number generator to create a list of 50 random numbers ranging from 1 to 100. So 1 through 75 represent a successful free throw because he says that he makes 75%. So if I'm looking at numbers 1 through 75, 75% of those numbers are numbers 1 through 75. So anything that's 76 to 100, that represents missed shots. So if we look at these numbers, most of them are low. So I'm actually going to do this by counting. So we're just looking at how many of the numbers are successful free throws. So numbers 1 through 75 represent successful free throws. So we're counting those. Okay, so that gives us, I counted an extra 182 wasn't one. So that gives us 39 successful shots. So in this simulation, there were 39 successful shots out of a list of 50 random numbers. So 39 out of 50 is 0.78. So that's 78%. Okay, so in the simulation, if I assume that somebody makes 75% of their shots, 78% would be a reasonable outcome, right? They can make it a little bit better than that. So then if we look at this sample distribution, so they did 50 more trials of the 50 shots to see what their number of successes were. And so what's happening here is that the average is that 0.75, right? So the middle is there at 0.75. So if we're looking at the range that contains 95%, so we're going to look for and select a range centered about the mean. And contains about 95%. And remember that since we have 50 trials, that's about 47. Okay, so what we're looking for is where can I find 47 results, and that's going to create my reasonable range. So if I look at this, so there were 16 that were 38 successful, there were 9 that were 37, and then if I make that go out a little bit more, there's 9 more. Then there were 12, then there were 8 here. This one has 11, this one has 10. So remember that I'm trying to figure out where can I get about 47 of these. So I'm looking for, if there's 50, I'm looking for to take off about 3, right? And so I should have done this from the outside. That would make this a little bit easier. But let's just continue from here. So this one has 3, this one has 5, this one has 4, this one has 1. And then this one has 5 again, 3, 2, 3. So if I want 47, then it looks like if I just cut off these last 2, right? If I look at that, that's 46. So if I take off the 3 and the 1 on either end, I could say that so that means that there's 46 between 31 and 43 successful shots. So 31, if we think about that, is 62%. And 43, if we think about that, is 86%. So what this shows us is that a true 75% free throw shooter would reasonably make between 62 and 86% of shots. So that means Alex percentage is probably not 75. He probably doesn't really make 75% of his shots because his free throw percentage in that one sample did not fit within that reasonable range. Okay, so this is looking at sets of data to find that reasonable range, that 2 standard deviations between the mean that contains 95% of the data values.